Okay, welcome back, my little linear algebra babies. So today we're going to be studying section 1.8, which is the topic of linear transformations or matrix transformations, and it's a extremely interesting topic. I think you'll enjoy it. We're going to spend this series. It's going to be a two-part video for 1.8. This first part we're going to formalize some of the vocabulary that we're going to use. The good news is you have actually used the majority of this vocabulary in your previous classes, only you've never really thought about your functions as mappings or transformations. So, for example, take the function f of x is equal to 3x squared. And I want you to really think about what is happening here. So, well, of course, the idea is you would have to choose some x value that you would plug in for x. You would then plug in, say, x is 1, into your function, 3x squared for x, and what would come back out would be, well, 1 squared times 3 is 3. All right, now this is old hat, but what I need from you is I need you to see further into what's happening here. So let's take that x is equal to 1 that you decided to plug in. So here, let's just say here lies, actually we'll use the 1 underneath it. So here lies x is equal to 1. Now notice that what you're doing is you have this one-dimensional number system of which there is no exclusions for which value you can choose for x. Right? So that's what we mean when we say the domain. I'll come back. I'm going to write a little bit more about this in just a second, but you were able to take a number on a one-dimensional number line, right? So we would think about this number line as being in R1 space, one dimension. And through a means of transformation, you were able to plug in a 1 and get back out a 3. So hold on here. So now what I need you to see is that you actually transformed from a number from a R1 dimension into an R2 dimension. Right? So, how did you do that? Like, so notice this blue line that I drew. So I have two different graphs, a one-dimensional graph and a two-dimensional graph. And the only way that you can get from a one-dimensional to a two-dimensional graph, the only way that you can get a 1 to become a 3 is if it undergoes some type of transformation, right? Now, I'm going to use a couple different words for transformation. I'm going to use word transformation. I'll go ahead and write it. Or rule, or mapping, or function. Now, I'm not saying that these are synonyms, but I am saying that in many respects they are interchangeable. So a function is what? A function is a rule. Now, our function, f of x, the rule is 3x squared. In other words, we operate on x by first squaring it, and then we multiply it by 3. That's the rule. So that when you come along and chose x equals 1, that 1 undergoes some type of transformation right, that we're going to call, that we label f. And what comes back out is a number which we're going to say f of 1 equals 3. Okay, now I just wanted to take a second and point out that you actually have been doing transformations all along, ever since, you say, algebra class. But the types of transformations that we're interested in are matrix transformations. So, for example, what happens if I take a vector and multiply it by a matrix? How does that change the vector? Do we go from R1 to R2, or R2 to R4, or R4 back to R2? Those are the types of things that we are considering right now. But first, again, let me not take for granted certain key aspects from your lower math classes, and then what we'll do is we're going to find the analog for these matrix transformations, and then see if we can connect all these dots. Ready? So let's make sure we understand the real number system. So now at this stage we're focusing on only the real numbers, so the numbers that lie on this this axis above, from negative infinity to positive infinity, which makes up the bulk of the numbers that you use every day. I said bulk. It makes up, I would assume, unless only in special circumstances, but it makes up every number that you could think of, pull out of the top of your head, should be located somewhere on this number line from negative infinity to positive infinity. We're not limited to this number line, but we would have to venture from the real number system. We would have to establish some more rules. So, for example, the square root of -1, and we could then start thinking about numbers in 2 dimensions instead of 1 dimension. But for this class, for this the purpose of this discussion, we are only concerned with the real number system. But what is the real number system? Well, we're going to start with some definitions here. So the first bullet is natural, a natural number. So what is a natural number, which we're going to label n? And I'm going to put an n right here. Now, instead of trying to formally define it, I'm just going to give you some a working definitions, just some examples of what we mean when we say natural numbers. So what would live in this little box that we're going to label natural numbers? Well, we can think of them as the counting numbers. So 1, 2, 3, so forth. No fractions, no zero, no negatives, just the counting numbers. Now, as we venture outside the natural number set, we can add to the natural number set by simply using, we could say, thinking of another number, which we're going to zero, such that we have, apologies, what's so funny is my wife and my 2 kids are having an incredibly competitive Monopoly game going on in the background. So I'm listening to them argue over the rules of the game, and I'm distracting myself. So what was I saying? So natural numbers are just your counting numbers. 1, 2, 3, ad infinitum. We're then going to add the number 0 to our set. So now we have 0, 1, 2, 3. And when we do, we have a new definition, a new term, which we're going to label W for the whole number. The whole number. So just notice that we have a set within a set, right? We have the natural numbers would be, we would say they are a subset of the whole numbers. And let's continue. So now what you've decided to do, if you want to kind of follow along with me, you have a few different numbers on this number line, right? 1, 2, 3. We even have 0. But remember, we're trying to fill in this. We want to fill in all the dots. So let's continue. So now we're going to go to integers, which we're going to use I. Now, the integers are going to allow us to deal with negative numbers, right? So we're on the left side of 0, if you will. So now we have things like -3, -2, -1. But again, the whole numbers is still within the integer set. The natural numbers are still within the integer set. So we still have 0, 1, 2, 3, of course. So bear with me. Let me write the things that in these boxes that I'm writing off to the left. All right, and now we're kind of just filling in as we go. So now we actually have some negative numbers. All right, we still have holes, right? Obviously we have holes in our number line. The last, the second to last set that we're going to talk about within the real number system is what we label as rationals, right? And to rationals, just think about the root here of ratio, right? To be able to write as a fraction. Now, to write something as a fraction requires that it have one of two conditions. Either it has a predictable pattern, right? So for example, 1/3 has a predictable pattern, although it doesn't terminate, it continues, but it does have a predictable pattern, or it actually terminates. So for example, 1/4, 0.25, that doesn't continue forever. That does terminate, and we can again think of it as a fraction. So I'm not going to stay here very long because I would assume the majority of you would know everything that I'm saying right now. At least you should. So now what we have is with the new set, the rationals, we now have the fractions that are in between these whole numbers, integers, natural numbers. So we have the stuff the stuff in between. And finally, we need to consider those numbers that are on this number line that cannot be written as a fraction, right? So, for example, pi, or the square root of 2. These are numbers, just like 3 is a number. They are numbers on the number line, with the only condition or the only caveat is that they cannot be expressed as a quotient of two numbers. Remember, they cannot be written as fractions. They do not terminate, and they don't have a predictable pattern. So if you have some time on your hands, you could always venture to YouTube, and I believe there was an individual who, I may butcher this, so you would have to correct me if I'm wrong, but I believe there's a video of an individual quoting pi, 3.1415, forever, out to about 50,000 digits. So this individual, I think it's about a 4 or 5 hour long video, and this individual they say they have a timer, and they just say, and they have a few people fact checking, and they say go, and this individual's like, okay, 3.1415, and they just continues for 4 or 5 hours. Now, I don't think you should watch all 5 hours. I watched all 5 hours, but that's me. But you can, if you want to see what I'm talking about when I say an irrational number. So again, let me go ahead and write IR. Okay, now that we have all of these sets, we could fill in this number line. It is so. Let me go ahead and continue in our work with linear transformation. So what I want to do here is I want to build on some vocabulary that you have dealt with before. Okay, I want to really formalize some ideas of what do we mean by domain and range. Now, some of these you may not have seen before. Things like codomain, or image, or function, or transformation. So let me go ahead and start. So down at the bottom, I have my list of terms, and then down at the bottom, I have this working example. And so I want to make sure that that you can see it as we go along. So recall that we chose, I believe it was x is equal to 1, so that f of 1 was equal to plugging 1 in on 3. All right, so let's start with the domain. All right, let me write this. So what is it? What do we mean by domain? Well, since it's I'll be a little bit informal, and I'll try my best to mix formal and informal. This informality and formalities. So domain is the set of allowable inputs. So what do I mean by the set of allowable inputs? So let's take a look at our, again, you'll have to always follow me but down to the bottom, right? Every single time you're going to have to follow me down here because this is where I'm looking at. So setting up our, so let's start with this first circle. We're going to call this circle, we'll just label it A if you'd like. But this little circle here is going to represent our domain. Right, and now let me read the definition. So the numbers that live in this circle is the set of numbers that we are allowed to input into the function that we are dealing with. Right, so thinking of 3x squared, there are no restrictions that we need to worry about if we're going to stay within the real number system. Right, we do not have to worry about. And we are staying in the real number system. So we don't have to worry about square roots of negatives. We don't have to worry about division by 0. So our choices of what we could choose to plug into our function span the real number system, right? So 1 obviously lives in this set, as does 2, as does 3, and so forth. All right, so now what about, let's do the codomain. What do we mean by codomain? Okay, so let's imagine just for a second that all, how do I want to put it? Let me just write it here first. So the codomain is the set of all, the set of all real numbers Now, what I mean by that is every real number from negative infinity to positive infinity all exist within the codomain. Now, that doesn't mean that based on the function that you have, like based on the definition, the rule, the function, the transformation that you have defined, that doesn't mean that you can reach every single number in the real number system, right? To make this point a little bit clearer, let's compare our f of x equals 3x squared to something like f of x is equal to well, let's just say 3 over x. Now think about this for a second. In our scenario, does 1 exist in the domain of our function? Well, yes, of course. 3 divided by 1 is 3. That's fully defined. Does 2, does 3, does 4? Of course. Well, so I'm gonna erase this. So can I put a 0, the number 0, in this set right here? That is the worst looking 0 ever. Let me try that again. So what about the number 0? Is that within our set here, our set A, which were the domain? Well, not of the second function, clearly, right? But what about the codomain? Well, the way you have to think of it is the codomain is all the real numbers, all potential numbers that you could reach. But the range is going to be all the actual numbers you can reach based on the function. So finishing up is the set of all real numbers that could potentially be reached. That doesn't mean you can reach every number. It just means that these are all the possibilities. Now let's do the range. And when I write the range, it'll start to click, the difference between codomain and range. All right, now, for our purposes, I think it's going to be better to get rid of this 3x squared because this guy has no restrictions on it, so it's not really doing us any good to continue to think about it. And I think I am going to focus on simply f of x is equal to 3 over x. All right. So I'm going to go ahead and put just like I had before, I'm going to put a 1 and a 2 and a 3 in my domain. Of course, those are allowable inputs. Over here, I'm going to have my range. All right. And let's see if this makes sense to you. So it's kind of hard to do. But I'm gonna box in, and let's think about all the real numbers that exist are in this box. Okay? All real numbers are within this box. However, what exists within the circle is the domain, the range. So this range, so I think my sincere apologies. I'm learning the technology as I do the technology. So this in here in my circle is my range, and this large square is going to represent my codomain. Okay, so now, ready? Are you back? Or come back to me. I think I got it. I think I know how to explain it now. So does the number 0 exist in my codomain? Absolutely. But does the number 0 exist in my range? No. Right? You can't, what are you going to do? 3 over x. You're not going to be able to choose a value of x such that 3 over x is equal to 0. So this is a no, right? 0 is not in the range. It is in the codomain, but it's not in the range. Now that, I think, will help clear some of this confusion up. Now, other than 0, what else is in the range? Well, of course, 3 is in the range. Of course, 1 is in the range, and so forth. But now the question becomes, how do you get to it, right? So let me come back over here to my domain. And the question is, if you want to leave one set to another set, Well, you need a transformation. You need a function, a rule, some way to map, right, from one to the other. So I'm going to go ahead and write what I said for range. So in this case, we're going to say the range is the set of all numbers, or let's say the set of numbers that can be reached from the domain. All right, that can be mapped to or reached given the domain. All right. So 0 was not in the range. It's just you cannot map from f of x equals 3 over x to 0, right? Does not exist. All right, so continuing in my vocabulary. So what do we mean by image? Well, maybe I can think of it this way. So I've already circled 1. And now let me go ahead and show you what I mean by, I'm basically going to answer the question of image and transformation all at once. So if I were to choose, right, x is equal to 1, I would plug in to my function. So this is f, right? That function would operate on 1, which it would transform 1. So 3 divided by 1 is 3. And notice that we're mapping. We're mapping 1 to 3. Now, if I were to choose 3 as my input into my function, well, 3 divided by 3 is 1. So again, notice that you're mapping from set to set. So now we're going to be mapping from 3 to 1. And what I'm showing you there is that mapping is what we label the image. It's a single number. Okay? So an image is a single value after the transformation of f. Right, so when you're used to saying f of x equals, right? So in this case, we'll use the very first one. So in this case, f of 1 equals 3. That's our image. Okay, that is the image of, or the image after the transformation f. Now, a function, I know you know how to use functions. Listen, I know that this is boring. I mean, you have to think about it. How could I possibly make vocabulary interesting? But we're going to move this, we're going to move to the matrix analog of this in just a second. So if you don't quite grasp what I mean by domain, codomain, range, image, you're going to have to either back up a little bit and rewatch it, or you might have to, reference your book or some other resource. But you want to have a good grasp of this vocabulary, because here in a second we're going to talk about, instead of f of x, we're going to be talking about matrix transformations. And so I need you to have a good grasp of this vocabulary to understand that lesson. Now, a function, right? A function, f, is just the rule that we use to map. So f, that's our function. Not f of x, right? It is true f of x, because we have the input of x. But the function f is the rule that transforms the domain of all x to f of x. Right? So f is the function. It is the rule that transforms x's to f of x's. So it transforms your domain to your image. It transforms a 1 to a 3. It transforms a 3 to a 1. All right. Now, the notation in this case, remember I just showed you a second ago how you're mapping from R1 to R2 by some rule. So I'm going to show you the notation, that the way you would notate that is f. We would think about f as the transformation from R1 space to R2 space by what? By f of x is equal to 3x squared. Okay? So we plug in values of x, get back out values of f of x. Let's keep rocking. Let's see if we can make this come alive a little bit more with one more example before we do our matrix transformations. Ready? So let's now see if you actually were listening to anything I said. So look, we have set A, we have set B. We have a rule. Now, I understand we're using T instead of F, but hold on. So we have set A, we have set B. And to this, we want to answer a few questions. As what's the domain? What's the codomain? What's the range? Now, so in this case, for my drawings, let's start with set A. So the only numbers, right, I'm looking here. So the only numbers that exist in this set is the numbers 1, 2, 3, 4. The only numbers that exist in set B is the numbers 1 through 10. Nothing else exists. With me? So no other numbers exist in either of those sets than what I've written. So we'll forget about the rule really quickly. Let's actually answer the question of what is the domain. Well, in this case, there are only 4 elements in this set, right? The cardinality of 4. The 4 numbers would include 1, 2, 3, 4. 4 elements exist in set A. Now, how many elements exist in set B? Well, we can write them. That would be the codomain. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay? All of those numbers are in set B. Okay? But now let's talk about the range. So to talk about the range, we're going to have to come back up here and think about how we get from one set to another set. So listen, you can't leave set A into set B without some type of mapping, right? You have to know how to map from one set to the other. Now, the rule here is what tells us how to map, right? So this is T. This is the transformation. Now, it appears that the way we've defined our transformation is, let's see if we can, I'm right here. So our inputs of X are then mapped to our outputs of 2x plus 1. Now, so we input an x, and what comes back out is a 2x plus 1. So let's try that. So if I input 1 into my transformation, well, 1 times 2 plus 1 is 3. So we have 1 mapping to 3. If I input 2, well, 2 times 2 is 4, plus 1 is 5, so I have 2 mapping to 5. And so forth, 3 times 2 plus 1, I have 3 mapping to 7. And finally, 4 times 2 plus 1, I have 4 mapping to 9. All right, so 1, 2, 3, 4 that exist in set A undergo a transformation of 2x plus 1, and the outcome is what? It is the range. So in this case, the range would be 3, okay? I'm going to be writing all the numbers that I circled in set B. So 3, 5, 7, 9. All right, beautiful. So now let's, this last little part says fill in. So in quotation marks, it says 3 is the blank of 1 after blank. So 3 is the, ready? Looking back at your vocabulary. So 3 is the image. It is the image of 1 after, well, after transformation T. Right? So this is the number 1, and when the number 1 looks in the mirror, the image that he or she sees is 3 after transformation T, right? That is the image of itself from that transformation. I hope that makes sense. All right, and so where are we in this process here? So, well, now we have to, now we actually have to take this, these vocabulary, this set of vocabulary, and we have to extend it to the ideas of matrices, right? So the main questions that we're going to be asking is the questions of how does, or how, let's think of it, let me write it. The main objective is how do we think about AX plus B, right? Where, so A is some matrix and X is some vector. And now you can, now we're going to think of it as just like, just keep thinking f of x. Keep that in your mind off to the side. So what's going to happen is just like in the previous example, I would plug in 1 for x and something would come back out for f of x. In this case, I have some vector x, and then I'm going to multiply that vector x by some m by n matrix A. And what I want to know is, I want to think about the mapping, right? B is the result, what comes back out after that matrix transformation. So let me see if I can take all of these terms and build, or basically extend the vocabulary to the ideas of linear algebra. Okay? So let me go ahead and get started. So in this case, x is a vector. And a vector in what? A vector in Rn. Right? So Rn space, nth dimensional space. Okay, now t of x should also be a vector. Right? So if you think about, again, you will have to continuously think about things like f of x equals, right? And you got to think about the input, x is the vector in Rn, and then what comes back out after the transformation will be a vector in Rm. All right, now, so in this case, matrix A is, or let's say A is an M by N matrix. And let me continue here. So T, what do we think about T? So T is the rule, right? Just like F is the rule. So T is the rule that transforms all of vectors x to T of x. Okay, let me give myself a little bit more space here. So it's the rule that transforms all vectors x to T of x. All right. Now, what about this idea of Rn? And what about this idea of Rm? Well, in this case, just like we can think of Rn as the domain of your, right, is the domain, the set of all x's that can be transformed by T. So Rn is the domain, right? It's the set of all x. Now remember, x is a vector. So all x that can be transformed by T. Okay, and to stay there for just a second, you have to think about, remember, there's some basic rules of multiplication when you're dealing with matrices. Right now, of course, this time it's a it's going to be an M by N matrix, right? A multiplied by an n by 1 vector, right? So a column vector. And if you recall, what happens here is there's some structure to this multiplication of matrices. And the structure is such that what I've just circled right now, those have to match. The number of columns in A must equal the number of rows in your vector X. Otherwise, structurally, you don't have a way of multiplying those two. Now, it didn't have to be that way, right? I mean, this is, again, and to any mathematician worth their salt would tell you that we didn't have to define this the multiplication of these matrices this way, but as always, normally in math, you start with a goal and then you define your operations to reach that goal. So this is the structure that was built, right? We can think of it as a consequence of some ideas, some premises that were put forth. Of course, the outcome in other words, if these don't match, you cannot do that multiplication. Just like when I had, my apologies, I'll erase this. Just like when I had f of x is equal to 3 over x. X was not within the domain of our function, right? And same way, if structurally, if in the columns of A don't match the rows of X, well, you don't have the structure to multiply. So that's a way we can think about the domain. Last, we're moving along. So how would you think about, well, Rm? Okay, so remember, the codomain was, if you think about it, the codomain in this was 1 through 10. You couldn't reach all 1 through 10 through that function, through that transformation. But the codomain was the numbers 1 through 10. So in this case, Rm is how we represent the codomain. The codomain of T. Right? It's the set of values that could come from the transformation. Okay. Now, I wrote T of X up here. I just want to go ahead and say a little bit more. That would be your image. And lastly, I just want to touch on two things, the notation, and I'd also want to touch on what do we mean when we say range. So 2 more definitions, and then I'll end this video and we'll pick back up at another time. So the range, again, just although the numbers 1 through 10 existed in set B, there was only 4 numbers that you actually could reach, right? And that was the numbers 3, 5, 7, 9. So in this case, let's again, the matrix analog to that, the range would be the set of all T of X right? Or it's the set of all the images that can be reached. So, all right, and finally, notice that just like in that previous problem, we were mapping x's through a rule of 2x plus 1. And this is, again, how we can think about our transformations, in this case, for matrix transformations, as a mapping from Rn to Rm, right? It indicates that the domain of T is the Rn and the codomain is Rm, is kind of what I mentioned prior, but that's the mapping. That's the rule that we're going to be using when we do some matrix multiplication. All right, so the preliminaries are out of the way. I hope that you were able to hope you were able to survive that. When I come back to the part B, we're going to just jump in and actually start doing some matrix multiplication. I will continue to use the terminology that we've established in this video. So if I say a vocabulary word and you don't quite recall what I meant by that, you might have to either look back up some of your terms or vocabs from this video.